Sir,
Yes.
may I just ask a quick doubt from one sum that we did last class?
Yes, yes, sure, sure, but
It was y equals to 1 plus 4 sine x plus pi by 3.
y is equal to 1 plus,
4 sine bracket
yes,
x plus pi by 3.
yes,
And we reached the step till sine theta will be um, greater than minus 1, less than plus 1.
huh, yeah.
And after that,
So
when
we
we
wanted
put
to find
the
the
value
global,
for,
we were looking for the global maximum minima, right, of this function?
yes, sir.
Okay, okay.
Yes, sir.
So, yeah, so tell me which is the step you had difficulty with?
So,
Yeah,
so after you put the value for theta in,
huh,
after that, on the minus 1 side, you put 1 equals to 4 minus 1. That I got. And then in the middle, where you had put sine theta value, you exchange it for y.
hmm.
So how did the y come there?
Okay, so the thing is what the method that we took now in that method, we replaced, let's say, x plus pi by 3 as a dummy variable, theta, let's say, right?
Yes, sir.
So we said that y became 1 plus 4 sine theta, right? So now we can
Yes,
say
sir.
that y's minimum value will be 1 plus 4 into sine theta's minimum value, right? And y's maximum value will be 1 plus 4 into sine theta's maximum value. Understood my point? Now?
Yes, sir.
Now we know that in general, sine theta is having this kind of range between -1 and +1. So this minimum will become 1 plus 4 into -1. So that is -3, right? And this
Yes, sir.
maximum will become 1 plus 4 into 1. So that will become 5. Okay. So that means here y is having a range between -3 and +5, right? So this was what you were having the difficulty with, beta, or another step?
So I got it practically what y means there, but isn't y that whole equation? So when we had just sine theta in the middle,
हाँ
how is y coming there?
नहीं,
Because y is 1 plus 4 sine theta, right?
हाँ तो वही बात है ना. So see what is happening here is that when sine theta is reaching the value of -2, है ना, then what is the value of y becoming? It is becoming 1 plus 4 into -1 na, at that instant, at that value of x. So like practically, let me explain to you here. So theta is how much? Theta is x plus pi by 3. Okay. So if we are saying sine theta is equal to -1, that means theta should be basically how much? It should be either, minus pi by 2, or it should be 3 pi by 2. Okay. And so on and so forth. Okay. So general solution will be like
Yes,
this.
sir.
So basically x plus pi by 3 should be equal to minus pi by 2 or 3 pi by 2 or such values. So that means x should become pi by 3 minus pi by 2, which you will see is minus pi by 6, or 3 pi by 2 minus pi by 3. So that is basically 270 minus 60. So that is 210, or that's basically how much? 5 plus pi by 6. So 7 pi by 6. So these kind of values. Okay. So let's see what is happening to y when x is one of these values. So y will become 1 plus 4 sine. So for example, if I take this value, minus pi by 6 plus pi by 3. Okay.
So it should be minus 5 pi by 6 instead
It
of
should be minus,
minus.
yeah, sorry, it should be minus 5 pi by 6. Correct. Okay. So when this is minus 5 pi by 6, so this is becoming actually 1 plus 4 sine minus pi by 2, right? So that is 1 minus 4 sine pi by 2. So that is 1 minus 4. So that's becoming minus 3. So now you're understanding, Sanvipita, how the value of y is becoming minus 3.
Yes, sir.
Okay. So similarly, when, for example, theta is equal to pi by 2 or 2 pi plus pi by 2, so that is so on and so forth, these values. What is the value of sine theta becoming? It is plus 1. So at that point of time, what is the value of x going to be? X's value is, for example, when this is pi by 2, x's value will become pi by 2 minus pi by 3. So that is pi by 6, and so on and so forth. So at that point of time, what is y's value? Y's value is 1 plus 4 sine. Now take this value of x. So pi by 6 plus pi by 3. So that's 1 plus 4 sine pi by 2. So it's becoming how much? 1 plus 4, or that's becoming 5. Okay. So that's how the value of y is reaching 5. Now the whole point is, whatever value of x we take, sine of x plus pi by 3 can never exceed plus 1. Okay. So we can say with confidence that this term 4 sine x plus pi by 3 will never exceed 4.
Yes, sir.
Okay. So that's why y will never exceed 5 now, because y is just 1 plus that much.
1 plus. Yes, sir.
Is it clear now? Right?
Yes, sir.
Okay. Yeah. So we were talking about local maxima and minima, apart from talking about global maxima and minima also. So hope those two terms were clear to all of you, the difference between global and local. Okay. Now in certain cases, the global might coincide with the local, and certain cases it will not coincide. So that we will understand with more examples also. Then we also saw the second derivative test. So we discussed about local maxima and minima. So as a definition, local maxima is the peak point. Is the value of y at a peak point. So the condition for this we saw is that f prime x should be 0 and second derivative should be negative at the point of local maxima. And similarly, we saw that local minima is like the dip point. So the condition for this is that f prime x should be 0 and second derivative should be positive. Okay. So this is the physical condition, we can say, or how we can find out the point of local maxima and minima using the calculus terms. Okay. However, what do we exactly mean by the peak point? So what we saw is that at a certain point, let's say x equal to a, if fx is greater than f of x plus minus delta x, okay, around it, where delta x is very small. So again, limit delta x tending to 0. So that means at that point, the function is reaching this kind of a situation. So the value of the function, the y coordinate at that point A, is greater than the y coordinate just to the right or left of it. Similarly, what do we mean by the dip point? So we saw that suppose this is happening at a certain point, x equal to b. So that happens if f of x is less than so that means the graph of the function at the point B be reaching this kind of a situation. Okay, so let's take a relook at these things with some examples. Find the local maximas or minimas and the values of x at which they occur for the following. Now you'll see that some of these functions are functions that we are familiar with from before. Okay. We have seen the increasing and decreasing intervals of these, but now we will not worry about those things, that in which intervals the function is increasing or decreasing, what is the the global maxima or minima, or any of these such things. We will just concentrate on what the question is asking, that what are the local maximas and minimas. So that means what are the values of y at the points where the function is reaching a peak or a dip, and at which values of x they are reaching this maxima or minima. Okay. So let's do this question with respect to that particular aspect. Okay. So we will solve it by what is called the second derivative test. We will not look at the intervals where the function is increasing or decreasing. We will look at that condition that we've discussed above, that f prime should be 0 and f double prime should be positive for minima and should be negative for maxima. Okay. So as I said, don't get into the full analysis of these functions. Don't get into intervals, don't get into domain, range, all those things at all. Okay. Just concentrate on what this is asking, that we have to just find the local maximas and minimas. That means we have to find the y coordinates at the point at which the function peaks or dips. And of course, we have to find the value of x at which it reaches maxima or minima. So just try this out and start sending me the answers. We'll discuss this. Yeah, Abhinav, but the thing is that there are more points at which there is minima. Okay, you have just pointed out one of the positions. Yeah, Prabhas, correct. You have to also give the values of x at which you reach the maxima and minima. Right. Ibrahim, correct. You have to also give the values of the maxima and minima. You're given the values of x at which you are reaching the local maxima and minima. But what is the value of the maxima or minima? It is nothing but the y coordinate at that point, right?
Yes, sir.
So you understand now? So if a function reaches a peak at a certain point, y is equal to fx, or ये वाला point suppose a है. So what we will say is that the local maxima equals to whatever the value of the function is at a, and it reaches at the point x equal to a. So the local maxima occurs at the point x equal to a, but what is the value of the local maxima? It is the value of the function. So it's the y coordinate at that point e. Now generally to find this point a, what is the method that we use? The condition that we discussed. Okay. So to find the position at which this is occurring, okay, we solve for f prime x equal to 0, and we find the roots at which f double prime is negative, or in the case of minima, f double prime is positive. So whenever we equate an expression to 0, the values of that expression at which it's equal to 0 is called the roots of the equation. So basically you can say that roots of f prime x are nothing but the critical points, the turning points, where the function might be having a maxima or a minima. Yes, Vedant, correct answer, but there's one more point of minima. Okay, there are 2 points of minima and 1 point of maxima for the first one. Same for you, Saina. Your values are correct, but there is one more point. So you'll see there's a total of 3 critical points. Yes, Ojal, very good. That's correct. Okay, so I'm just illustrating the steps of the first part for all of you to verify. So the function given to us in the first part is polynomial of degree 4. So that means that derivative of the function will be a polynomial of degree 3. So we can have up to 3 roots. Okay. And the second derivative will be differentiation of this. So that will be this much, right? So now we can see that f prime x is equal to 0 for three points. So x equal to 0, x equal to 1, and x equal to -1. So these are what we can call the turning points or critical points. So turning or critical points are points at which the slope of the function is 0. So they are either local maxima peaks or they are local minima dips. Now each of these points we have to investigate for the second derivative. So at x equal to 0, you can see that f double prime is going to be how much? It's going to be 0 minus 4. So it's negative. So that means at x equal to 0, the function has a local maxima. Okay, and what is the value of the maxima? It is f0. So it is plus 1. So the local maxima's value is equal to plus 1. And it occurs at the point x equal to 0. Similarly, at x equal to 1, we can see f double prime 1 is 12 minus 4. So it is positive. So that means at x equal to 1, the function has a local minima. And the value of the local minima is f1. So that is 0. So local minima is equal to 0. Okay. And it occurs at which point? At x equal to 1. So same thing you will see for minus 1 also. Okay. So in fact, you will see that there's a symmetry here. So at x equal to minus 1, you do all this analysis, you'll get the function has a local minima again. So interestingly, it's a recurring local minima equal to 0 at x equal to minus 1. So these are the steps we have to repeat in each of the questions.
So how is local maxima coming as positive 1 and 0?
Yeah, so see, we are understanding that local maxima is occurring at which value of x? At x equal to 0. So for the function,
Yes.
what is the local maxima? Is the y coordinate at the value of x equal to 0. So in fx, we will substitute the value of x as 1. So it is f of 0. You understanding better? So f of 0 is how much? 0 to the power 4 minus 2 times 0 square plus 1. So that's 1.
Oh, okay, sir.
Got it now? Okay. So
Yes.
similarly, now we know minima is occurring at which point? Local minima. One of the points of local minima is plus 1. So substitute the value of x as plus 1 in the expression of the function fx. So f of 1. Now that is how much? 1 minus 2 plus 1. So that's 0. Okay, so hope this part is clear to all of you.
Yes,
So I'm
sir.
going back to the question now. Okay, the rest of the parts. So I want you to find the local maxima and minimum of x plus 1 by x also next. Yes, Prabhas, your analysis of second one is correct. Third one, there is local maxima minima beta. Abhinav, your values are correct, but the interesting thing about the third question is, about the second question is that at the point 1 we have the local minima, and at the point -1 we have the local maxima. So when you look at the values, what I'm saying will seem a little confusing. Okay, but nonetheless, that is the truth about the function, and we will discuss in detail the reason why that is happening also. Apart from, of course, the condition of local maxima and minima. Okay, so the second part's answers I'm just giving for your reference. We'll discuss also soon that there is a local maxima equal to -2 at x equal to -1, and there's a local minima equal to +2 at the point x equal to +1. So at this stage, it might seem very strange to you that there's only one local maxima and one local minima. So how can it happen that the minima is actually greater in value than the maxima? We'll discuss about why that's happening also soon. Okay. So this has a local maxima of 1, which was occurring at x equal to 0, and a local minima of 0, but that was occurring at 2 points, x equal to 1 and x equal to -1, repeated. Okay. So I'll discuss the solutions of these also soon. Okay, just I'm waiting for all of you to try out these questions. Okay, so you have got the same thing by the steps, right, Abhinav?
Yes, sir.
Okay, good. Now, when you look at the values, it does seem strange, ना कि कैसा हो सकता है कि local minima ज़्यादा बड़ा है and local maxima is lower. But one hint to you, which I'll explain later in detail also, is that the function's graph is not continuous because it's not defined at x equal to 0, na? So it's not like a continuous curve. There's a break in the curve. So that's one of the reasons why this is happening. Okay. If you have a continuous curve which has only one maxima and one minima, And this cannot happen. If you have a continuous curve, then obviously the value of the maxima has to be greater than the value of the minima. But this one is not a continuous curve. There's a break in the curvature because x equal to 0, y cannot be defined. So that's partly the reason why this strange phenomena is happening in this, that the local maxima has a smaller value than the local minima, and at the same time there's only one local maxima and one local minima. Okay. Now the third one, the solving part, you might think is a little more lengthy because you have, for derivative you have to find you have to use the quotient rule, and second derivative to differentiate it becomes even lengthier. But nonetheless, once you do the analysis, you will see it's simple enough. Okay. If you also notice, there's a connection between the second function I've given and the third function. The third function is like 1 upon for the second function. The second function is x square plus 1 whole divided by x. The third one is just inverse of that, x upon 1 plus x square. No, Prabhas, better. Maxima and minima points will be 1 and minus 1, but the values will be half and minus half for the third one. So I'm just putting up the answer. I'll discuss the full solution. So this will have a local maxima equal to half, but occurring at the point x equal to 1. And this will have a local minima equal to minus half, which is occurring at the point x equal to minus 1. Okay. Just be careful with the differentiation part. Quotient rule and all you can use for differentiation.
So can you start the third one?
Yes, Aryan, that is correct about the fourth one. Okay, so now I'm doing the analysis of all these questions in detail. So let's start with the second one. So for this function, the derivative is 1 minus 1 by x square, and therefore the second derivative is differentiation of this, so that will become differentiation of minus 1 by x square, so that is 2 by x cube. Right? Differentiation of 1 is 0, differentiation of 1 by x square is minus 2 by x cube, so minus 1 by x square's derivative will become this. Okay, so make sure these steps are clear. Okay, now for local maxima and minima, or for basically critical points, okay, derivative should be 0. That means we are finding the roots of this equation. So x equal to plus minus 1. These are my critical points. Now in each of the critical points, I have to do the second derivative test. So critical points are basically roots of f prime x. So roots of f prime x basically means this step next. Okay. Now from here, next thing we have to do is the second derivative test. That is the values of f double prime at each critical point. Okay. So let's start by x equal to 1. F double prime of x equal to 1 is how much? It is the value of this function. So it's 2, which is positive. So therefore the function has a local minima at x equal to 1, and the value of the local minima is f of 1. So it is equal to 2. Because remember the function is x plus 1 by x. Okay, so it has a local minima equal to 2 occurring at which point? At the point x equal to 1. Now similar second derivative test you repeat at x equal to minus 1, and you will see that it will be a point of local maxima, but the value of the local maxima will be minus 2. So as I said, this will seem strange that how the local maxima has a value minus 2 and the local minima has a value 2. So that also we'll discuss in a bit. Okay. But as far as this question, the way it is asked is concerned, the problem is over. We were just asked to find local maxima and minima and the values of x at which they occur. So they are this. Okay, so you repeat the second derivative test at x equal to minus 1. You'll see that f double prime of minus 1 will come out to be minus 2. So that means the function has a local maxima. So the value of this local maxima Okay, let's come to the third one. So derivative of the function will become denominator into differential of numerator minus numerator into differential of denominator divided by the denominator whole square. And second derivative is now going to be pretty complicated. The denominator into differential of numerator minus numerator into differential of denominator, which you can differentiate by chain rule. Divided by the denominator whole square.
Sir, the question is 1 plus x the whole square or 1 plus x square?
1 plus x square, na beta? Yes, na? See? ठीक है ना?
Okay, sir, I think I missed it.
Acha, you took it as 1 plus x whole square in the denominator. That's why you were not getting
Yes.
the answer, na? Okay, now it's clear. Okay, so f double prime is pretty complicated, but this is what I'm getting. Just check my calculation.
Yes, sir.
Prime, you got the same?
Yes, sir.
Okay. So once you've got f prime x and f double prime x, we can now concentrate on analysis of critical points. Okay. So for critical points, they're basically roots of the derivative. So basically, now you can see in this expression, the denominator is a positive term always for all values of x. So that means the whole function is, the whole expression can be 0 only when the numerator is 0. So again, x is plus minus 1. These become our critical points. And while the expression of f double prime is rather lengthy and complicated, but you'll see it's very easy to analyze at the critical points. You'll see at x equal to 1, you will get f double prime's value as negative, and at x equal to -1, you will get f double prime's value as positive. So we can, have a situation where the function is such that executing the differentiation will become a bit lengthy, but nonetheless, in terms of what we are trying to achieve, it's the same thing altogether. Okay, that derivative, then second derivative, then analyze the derivative for its roots. Those are our critical points. And at each of the roots, analyze the value of second derivative. If that is negative, then that is a point of maxima. If it is positive, then it's a point of minima. It's a simple algorithm, always. Okay, so now we can analyze at x equal to 1, f double prime 1 is how much? It is 1 into -2 divided by 8, right? So basically it's a negative value. That means f1 is a local maxima. What is f1? F1 is 1 upon 1 plus 1 square. That is 1 by 2. So at x equal to 1, we have a local maxima equal to half. Similarly, at x equal to -1, the value of the second derivative, you will see, will come out to be -1 by 4. Oh, I think I made a mistake in the value here, but it doesn't matter, plus minus. This is 2 into 1 to 1 minus 2, or 1 minus 3, so it will be minus half. Okay.
So, did I miss the part where you put the values of x in the second derivative?
I'm doing that part now. Okay.
Okay.
F double prime of -1, I'm finding out now for the second critical point, x equal to -1. So what is the second derivative? This value. So in this, you put the value of x as -1. So see, you'll get -2 into -2 divided by 2 cube, right? So we'll get this as 1 by 2. So second derivative is what kind of quantity? It is positive. So that means we have a local minima. And what is the value of the local minima? It is f of -1. So put -1 back in the original equation. So the original equation, remember, was x upon 1 plus x squared. So it is -1 upon 1 plus 1, or minus half. So we have a local minima equal to minus half. At which point? At x equal to -1. Whereas we have a local maxima of plus half. At which point? At x equal to 1. Yes, Ojal?
So I have a doubt that if can't we just calculate the for maxima the slope goes from plus to minus. So
we can do that also. Yes, we can.
There won't be any need to find the prime second derivative.
The second derivative, no?
Yes, sir.
Yeah, so you can do that, but see, generally it is easier to find the second derivative than do the analysis of increasing, decreasing. You understanding the point, beta?
Yes, sir, but I like.
But in this particular,
draw a number line and then just mark them all, and then we can just find.
Yeah, so in this question, it might be easier to do that, to do the analysis of increasing, decreasing, right?
Yes, sir.
Yeah. So there's always a trade-off. In certain questions, the second derivative is very easy. Like for example, the first question that we did, the polynomial of degree 4. In that, rather than solve the whole inequalities and mark the number line and all that, it's easier to just quickly work out the second derivative. In this question, on the other hand, second derivative is very cumbersome to calculate. So that number line method might be easier. Okay, so hope the analysis of this was clear. Now let's come to the fourth one. Now this is probably the easiest of the lot. Okay, so derivative of the function will become by chain rule differentiation of e raised power x square will become e raised power x square into derivative of x square, that is 2x. Okay. So critical points. Now second derivative is also equally easy. Differentiation of 2x into e raised power x square. So that will become 2 into e raised power x square plus 2x into differentiation of e raised power x square, which we have seen as 2x e raised power x square. So this is our second derivative. So now f prime x equal to 0 for our critical points. That means 2x has to become 0 because e raised power x square, as you can understand, is always a positive quantity. Okay, so x equal to 0 is our single critical point. Second derivative test now.
Sir, can you explain the e raised to power x square again for the turning points part?
Derivative 2x e raised power x square, this point is clear, na? F prime x kaise aaya?
Yes, sir.
Okay. Now critical point kya hai? Where the derivative is 0. So I want 2x e raised power x square to become 0. So what point of x will satisfy that? So it's the product of two things. Matlab 2 is obviously a positive number. So the product of this into this should be 0. So either this should be 0 or this should be 0.
Yes.
Okay, or both are 0. But now you can see the quantity e raised power x square is never 0. Because e raised power, matlab, it's basically x square is ranging between 0 and infinity. So iska minima kitna hai actually? Iska minima 1 hai. और इसका global maxima कितना है? E raised by infinity or tending to infinity. So this term e raised by x square is always ranging between 1 to infinity. So it's never going to hit the value 0. So it's only x equal to 0 is the single critical point. Okay, na?
Yes, sir.
Okay. Now second derivative test at this point, we can see that f double prime at x equal to 0 is nothing but this thing. So that is 2 into 1 plus 0 e raised by 0. So that is equal to 2. So it's a positive quantity. So that means at x equal to 0, the function has a local maxima. A local minima. Second derivative is positive, so it has a local minima. And it does not have any local maxima, this function. It has only one turning point, which is a dip kind of point. There is no peak kind of point. So therefore, we'll say that, so the local minima's value will be f of 0. So that is e raised by 0 or 1. So this function has a local minima of y equal to 1 at the point x equal to 0 and does not have any local maxima. That is the final conclusion over here.
Sir, I got stuck at the second derivative.
Okay. So that is something to get used to. Okay. So you'll be doing a lot of practice questions in local maxima minima. Okay. And getting used to this gradually. Okay. Okay. Now
No, sir,
having
can
understood
you explain that part, please?
which part, beta?
The second derivative.
Second derivative, we are just using product rule. No? See here, the function's derivative, the first derivative, it came out to be how much? 2x into e raised power x square. So second
Yes, sir.
derivative, we want to differentiate this term.
Yes, sir.
So I'm just treating this like a product of two terms. No? Like if this is u and this is v, then derivative of this is going to be u v prime plus u prime v like this. Okay. So first function, that is 2x into differentiation of e raised power x square. Now differentiation of e raised power x square just above only we have done, so we can just copy it. It is 2x e raised power x square plus derivative of first function. So 2x's derivative is 2 and second function is e raised power x square.
Got it, sir.
Okay, only thing is I think I made a mistake of value here. There's another 2 here, no? Because it's 2 plus 4. Okay.
Yes, sir. 4x square plus 2 e raised to power x.
Correct. So it should be like this. But nonetheless, it will not really make a difference to our answer. Yeah, it will not really make a difference to our answer even here. But just anyhow, just make a note of this correction here. Okay, so before we move on, just let's do a bit of analysis about these functions further than local maxima and minima. Okay, so graphs of each of these and behavior of the function. So this was our first function. Okay, now we saw that it has local maxima equal to 1 at x equal to 0, and it has local minima equal to 0 at x equal to -1 and again equal to 0 at x equal to +1. So it had two local minimas and one local maximum like this. Okay. Now we can see another thing over here that
x minus half and plus half, right?
नहीं बेटा ये वाला function था. The first one, see the.
Yes, sir. The minimas are at minus half and plus half.
Let's go back to this. Okay. The critical points were the roots of this equation. So they were x equal to plus minus 1. Right? I think you're confusing it with the third question maybe. Right? All right now. Derivative is this now. 4x cube minus 4x. So uske roots kya hai? 0 plus 1 and minus 1, right?
Okay, sir. Yes.
So these are the values. So I'm just taking these values below here. Okay. Now apart from this, now I will not do the full analysis of increasing and decreasing intervals. I'll just understand that okay, these points are there. Okay. Now what about the value of y as x tends to minus infinity? Y will tend to what? Y will tend to infinity here because x to the power 4 term dominates over x square term. And again, as x tends to infinity also, the value of y tends to infinity. So now I can visualize on the number line what is happening. 0, 1, -1. Okay. So the function is reaching a minima, okay, at 0. So it must be decreasing from infinity, reaching a local minima, then increasing, reaching a local maxima, then again decreasing, reaching a local minima, then again increasing and going to infinity. Okay. So from this, just this much only, I can analyze the graph of the function. That will basically have a W kind of shape. And I can see that the global minima itself is 0. That means for no values of x, y is becoming negative at this kind of a shape. So these are our critical points. -1, 0, 1, 0, and 0, 1. And those are also points of local maxima and minimum. Now, another way to justify this is also that you can also see that this can be written as, I don't know if any of you noticed this, this can be written as this.
Yes, sir.
So you can see that y is greater than equal to 0 for all x. Okay. And y is minimum is 0 for x square is equal to 1. So that means x is equal to plus minus 1. So algebraically also we could have analyzed this. It's just a coincidence that the function is a very simple one which we can convert into a whole square like this. So apart from local maxima and minima, you can also see that the domain of the function is -2 plus infinity. Okay. And the range of the function is all non-negative numbers. So there's so much more that we can understand about the function, but this time we have understood all this basically by just looking at local maxima and minima. We haven't really got into intervals and all that, right? Okay, now the second one is really interesting in terms of graph.
So 1 second, I just had to copy.
Yeah. So second one will show a very peculiar feature of the graph, which will also show the strange nature of the function, why the local maxima is actually a point at which y is less than the local minima.
Done, sir.
Okay. So for this, we had seen that we had a local maxima equal to -2 at x equal to -1 and a local minima equal to +2 at x equal to 1. But we also note here that the domain of the function does not include 0. That is, x should not be equal to 0. Okay. So now let us look at, for example, what is happening as x tends to minus infinity. What is the value of y? It will tend to minus infinity, because this term 1 by x will be negligible when x is very large in magnitude. So basically y is like equal to x. So when x is tending to minus infinity, y is equal to minus infinity. And similarly, on the positive side, when x tends to infinity, y's value also tends to infinity. Okay. Also, if x tends to 0 but positive, then what does y tend to? Y tends to infinity. Because now as x tends to 0, this term x is negligible. So y is like 1 by x. So, okay. But if x tends to 0 on the negative side, then y will tend to minus infinity. Now see something very interesting. You can divide the number line into two parts. What is happening before 0 and what is happening after 0. So before 0, what is happening is that it's going to minus infinity. But you can't take the point 0. And again, it's going to minus infinity on this side. But in between, it is reaching a local maxima at the point x equal to 1, minus 1. And on the positive side, you can see that there's a critical point of 1. So it is decreasing up to 1 and then increasing after 1. So it is reaching a local minima at x equal to 1. But at 0, it is like a not defined. So 0 is a disjoint graph that we will get. So that is what makes this a very interesting function. So when we visualize the graph now, we'll have to think of individual parts of the domain. The negative part of the domain and the positive part of the domain, because it does not include 0 now, the domain. So in the positive part, you can see this is what is happening. As x tends to 0, y tends to infinity. But then it drops to the value at 1, which is how much? 2, and then again increases to infinity. So the shape of the graph is like this. It's a very interesting shape. That is why, interestingly, this is a point of local minima. And similarly, on the negative part of the graph, you will see it has just like a mirror image kind of shape. That's why this graph has that strange feature that the peak point is actually below the dip point. At the same time, there is only one peak and one dip. This will never happen in a continuous graph. If a continuous graph has one local maxima and one local minima, it has to be either like this or it has to be like this. But this is a discontinuous graph. There's a break in the graph at x tending to 0 or at x equal to 0. So that's why this strange kind of phenomena is happening.
Sir, when a function is in inverse of the other, so the graph also is supposed to be the mirror image, right, along x is equal to y?
A mirror image with respect to x is equal to
Y.
Minus of x equal to y. So actually, technically in further advanced functions in maths, you'll learn that there are two types of functions: even functions and odd functions. Okay, so odd functions are the ones where f of minus x is minus of fx, and this you'll see is an example of an odd function. So in an odd function, what happens is that whatever the shape of the graph on the positive side, you draw a mirror image of it on the negative side and then invert it. So on the negative side, it's that kind of, okay. Whereas there are also functions which are even functions, where f of minus x is equal to fx. These are called even functions. And here, the left-right side are basically perfect mirror images. So our earlier graph of that, that power 4 function, this was an example of that because the powers were all even powers.
Okay, sir.
And then, of course, there are functions which are neither even nor odd, because there might be like a polynomial which has both even degrees and odd degrees in its power series, right? So that is
but I was
neither.
actually talking about the next question and this one. So the next question is inverse of this, right?
So one
if
of
I relate the graphs.
Right. So kind of you can understand how the graph will go. But then for the next one, x equal to 0 is not a point of discontinuity.
Okay, sir.
So yeah, I mean, algebraically they have the relation that whatever this function is fx, that one was 1 upon fx. Okay. So the peak and dip point are kind of getting inverted. That's true.
Sir, I was actually trying to relate it from an example. I think we solved it around a month ago.
Yeah.
So there was a function, and then we drew y is equal to x, and then we drew the graph of its inverse, and we found that they're actually
that is a
both the
different thing,
same.
but that is not 1 upon function. In fact, you know, when we have 1 upon fx, we should not use the term inverse. We should use the term reciprocal. Okay, so reciprocal is different to inverse. You understanding the point, Bhatta? Inverse of a function is like this. If we have a function y is equal to fx, the inverse of the function is f to the, f inverse x, like this. So this is not the same thing as reciprocal 1 upon fx. So for example, we have the function y is equal to x square. Okay, and we have the function y is equal to root x. So these are inverse of each other because x is equal to root y.
Yes, sir.
So if we look at the graphs of these two functions, they are mirror images about the point, about the line y is equal to x. So y is equal to x square has a graph like this. Okay, y is equal to root x. I'm taking only the positive part of the domain where we can compare them, is like this. Okay, and their mirror image about this, about the line y equal to x. Okay, or for example, you have the function y is equal to e raised power x. That means x is equal to ln y. So if you take the function y is equal to ln x, these two are inverse of each other. So if your fx is e raised power x, then inverse function of fx is ln x.
Okay, sir.
So again, their graphs have this relation.
So means if I invert the position of x and y, and if
exactly, if you interchange x and y, the domain and range get interchanged.
Okay, sir, I got it.
So this is that interesting thing. So if this is the graph of e raised power x, then the graph of ln x like this, and it's a mirror image about this. So anyhow, so here in this case, actually the next function is, properly speaking, we won't say it is inverse, it is reciprocal. So reciprocal graph does not have that property, right?
So please zoom out. I want to note this down.
Yeah.
Thank you, sir. I'm done.
Oh, okay. So let's come to the next example. So now we had this function x upon 1 plus x square, right? So for this, what we had seen is that there is a local maxima equal to half at x equal to 1, and there's a local minima equal to minus half at x equal to minus 1. Okay. Now we can also see in this that y is equal to 0 at x equal to 0. Okay. And also y tends to 0 at x tending to infinity, and y tends to 0 at x tending to minus infinity. Because always the denominator will dominate. So think of x like 10,000. So y is like 10,000 divided by 1 million. Sorry, 100 million. So it's obviously tending to 0. Or think of x as minus of 10,000. So y is minus 10 of 10,000 divided by 100 million. So again, it's tending to 0. So now if you try and think in terms of the number line, so your critical points are -1 and 1. Okay. Now the function in this case is rising, reaching a, oh sorry, it's dipping, okay, reaching a local minima of y equal to -half, and again rising to 0. Okay. Then it continues to rise beyond 0, reaching a local maxima equal to half. And then after this, it drops because it has to go to 0 as x tends to infinity. So putting together that information, now we can see that this function will have this kind of a nature. In the positive part of the domain, it starts from 0, reaches a local maxima, and then tends to 0 again as x tends to infinity. And it's just doing a sort of mirror image of that, but an inverted mirror image of that in the negative part.
So this is an odd function.
Yeah, this is an example of an odd function again. So this is our function x upon 1 plus x square. Now, also just for the analysis, just compare this graph with the reciprocal of this function, which we had seen above. The reciprocal of this function was 1 plus 1 by x, or sorry, x plus 1 by x, or x square plus 1 by x. So that was like this. That was also an odd function. But see, the point at which this reaches maxima, this one reaches minima. The point at which this reaches minima, this one reaches local maxima. There's an interesting correlation between their graphs. Okay, another thing you can see in the graph is that for the region of the domain where x is very close to 0, the graph is almost actually like a straight line passing through the origin, which is y equal to x. Because when x is very small, the denominator is almost equal to 1. So basically, the function is like y is equal to x upon 1 plus some negligible term. So it's more or less like y equal to x. So this part of the graph near about x equal to 0 is like a straight line y equal to x. But then, of course, as x increases on either side, the behavior of the function changes because x square becomes significant in the denominator. Similarly, as you go very far off along the x-axis, either positive side or negative side, it's like 1 is negligible compared to x square. So you can treat the function approximately as x upon x square or 1 by x. So the behavior of the 1 by x graph that we had seen earlier, same type of behavior this graph has for very large values of x or very large values on the negative side. But in between the behavior is changing. So it's like the behavior of the graph is changing from that of the linear function y equal to x to the hyperbolic function y is equal to 1 by x. So in between it has to go through some kind of a transformation like this. Okay, so this is just a collection of some interesting functions as far as analysis of domain, range, maxima, minima, etc. is concerned. It's not that, you know, in physics you are required to do so much detailed analysis in terms of graph and all that. But yes, in future we will see that when we are applying calculus in different parts of physics, we might come across a situation where we have to analyze how one physical quantity behaves with respect to another. So that is nothing but analysis of the behavior of functions. So these kind of concepts are important to understand. Okay. Also, for this function, we can see that the domain is x belonging to all real numbers, and the range is very limited. The range over here is only between -half and +half. So the global maxima and minima in this case are again coinciding with the local maxima and minima. Okay, now moving on to the final one. In this, like the question itself, the graphical analysis is also quite easy because we need not, you know, get into anything to do with derivative. We can just understand it from a point of view of the behavior of the original function. How does the exponential function's graph look like? We know that it has a range of 0 to infinity open interval. This is a graph of y is equal to e raised power x. So as x tends to -infinity, y tends to 0. As x tends to infinity, y tends to infinity. And this point is 0, 1. So at x equal to 0, y is equal to 1. Now compare that with y is equal to e raised power x square. Now think of this like y is equal to e raised power z, where z is equal to x square. So for all values of x, z is this. So what about e raised power z? E raised power z will only go from 1 to infinity. Because it's like this part of the, so the graph of the function will obviously be like, this is what we call an even function. The function's value at some -x is equal to the function's value at x. So you can see that this part of the domain is very similar to the graph. Only it will rise a little more rapidly because it's e raised power x square after all. Okay. But now this side will be like a mirror image about the y-axis because any value at -x is the same as the value at x. So obviously the graph of the function will be this kind of shape. So we are having one critical point, and that is a point of local minima. So we can see that x belongs to this interval. So correspondingly, y belongs to 1 to infinity. So as far as range is concerned, it is closed interval 1 to infinity. So the global minima is 1 and the global maxima is tending to infinity. Okay, now this is not the only thing for which maxima and minima is used, okay, to understand the behavior of the function and draw its graph and all that. Okay, sometimes very critical physics problems require the analysis of maxima and minima. So we will extend our discussion of word type of problems with differentiation used as an application in physical situations. We'll extend that analysis now to include situations where maxima minima also comes into play. Okay. So next we'll look at a very interesting problem from basically kinematics, but two objects moving and how they are related to each other. So let's say we have a situation like this, that on some kind of horizontal floor or horizontal road or whatever, at the moment t equal to 0, we have this situation. We have a motorbike which is at rest but sets off with a uniform acceleration. So uniform acceleration of, let us say, 2 meters per second square. And at the same instant, we have a car, okay, which is moving with a uniform velocity but has zero acceleration. So it is moving at uniform speed, b equal to, let us say, 10 meters per second. And at this particular instant, the distance between them, which is t equal to 0, the distance between them is, let's say, 50 meters. So now what we have to do is, first of all, express the displacements for the bike and the car as functions of time. Okay. Then from that we will express the distance between them as a function of time. So we'll take the distance between them as s. And we'll plot the approximate graph of s versus t and find the maximum value of s, okay, till the bike overtakes the car. So we'll analyze this graph and analyze its maximum value only up to that point when the bike overtakes the car. You'll realize that the car is going at a uniform speed, whereas the bike is accelerating. So definitely at some stage, the bike is going to overtake the car. It's first going to catch up with the car and then overtake it. So we are going to analyze the third part, the graph of s versus t, only up to that instant when the bike is about to overtake the car or it's just about started to overtake the car. So between t equal to 0, where this is the situation, and that instant when the bike is about to overtake the car, between those two instants, we have to analyze when the distance between the car and the bike reaches the maximum. So this is a typical example of now the application of calculus as a rate measurer or differentiation as a rate measurer and analysis of maximum minimum of a function. And notice again, in this, we will not say whether we are talking about local maxima or global maxima or what. We have to understand that from the analysis of the problem itself, right? Yes, very good, Janvi, Vedant. Your answers are correct. Okay, so we'll see that if we compare the situation at t equal to 0 with the situation after some time now, so at some time t, let's say the bike has reached here. So that this is the displacement of the bike. Car has reached here. This is the displacement of the car. So the displacement of the bike as a function of time, because it's uniformly accelerated, will be t square. And its initial velocity was 0. Whereas displacement of the car will be uniform velocity into time. So that will be, how much was the velocity? 20 meters per second, right? 10, sorry. So 10. So now we can also see that at this new instant of time t, what is the distance between the car and the bike? That is this one. So the distance has become the initial distance, which was 50 meters, plus, so s between them has become 50 meters plus displacement of the car minus displacement of the bike. So it has become 50 plus 10t minus t square. Okay. So this is the distance between the car and the bike as a function of time. Now, when we analyze this function, we can see that it's a simple quadratic function where ds by dt is 10 minus 2t. So we can see that ds by dt is positive for 0 to 5 seconds. ds by dt becomes negative for t greater than 5 seconds. Okay. So therefore, it has a maxima at t equal to 5 seconds. So we analyze the graph now. And we analyze only up to this point because S is equal to 0 at the instant when the bike overtakes the car. So we'll find out that value. Okay. But one thing we know is that this value of time, when the distance reaches the maximum before it overtakes, this value of time will be 5 seconds. That's much we know. So this maximum distance that will be there, that will be how much? It will be distance at t equal to 5 seconds. So it will be 50 plus 50 minus 25 from this, because S was equal to using this value, it will be 75 meters. So it will reach a maximum of 75 meters.
Sir, can you explain the last part again? The displacement.
The third part?
Yes, sir.
Okay, so see, third part mein ke liye, what we are doing, we want to plot the graph of S versus time, distance versus time.
Yes.
So in general, you can see it's a quadratic function, so it will be a parabola. And you have an idea that it will be a parabola pointing downwards because the coefficient of t square is negative, no? So it will be a parabola of this kind of shape.
Yes.
Okay, now what other information we have? That parabola has to start from S equal to 50 at t equal to 0. So this is the starting point.
Yes.
Okay, and wherever it reaches the peak point, the slope is 0. So put ds by dt equal to 0. So what point you get? 5.
Okay. Okay.
Now, you
Yes.
can see ds by dt is positive before 5 and negative after 5. So it's reaching the peak point exactly at t equal to 5. So then what is the peak point's value? So for that, substitute t equal to 5 in which equation? In S. So S ka value kitna hai at t equal to 5? It is this much. It is 75 meters. So that means for the first 5 seconds, the car is actually gaining distance over the bike, and the distance is increasing from 50 to 75. But from 5 seconds onwards, the opposite happens. The bike starts gaining distance over the car. So the distance between them starts decreasing. Okay. And you can see that at some stage it will even become 0. So for that, we'll have to find the root of this equation.
Yes, sir.
You understood this now? Okay. So for example, if you also correlate it with the actual on the ground physical situation with respect to the graph, what we are understanding, see, t equal to 0 pe, the bike is at rest. Okay. Whereas the car is moving at 10 meters per second. So what is happening? The distance between them is increasing at the rate of 10. So you can see from the graph that when you started out, S had a positive slope. So the distance was increasing. But for example, let's see what is happening at 1 second. At t equal to 1 second, okay, by now the bike has got some velocity. It has got a velocity of 2 meters per second, but the car continues to move at 10 meters per second. Because this had an acceleration of 2 meters per second square. So still you can see that the distance between them is increasing. Still you can see that this S is increasing. Okay, so still S has a positive slope. But like that, by the time you come to t equal to 5 seconds, see what's happening. At that moment, the bike is also moving at 10 meters per second. The car is also moving at 10 meters per second. Okay. So the distance between them is changing at 0 rate at that instant, at t equal to 5 seconds. You can see the slope of this graph is 0.
They're moving together, no, sir?
They are moving together but synchronized, but just for an instant. Na? Even at a microsecond after this, what is happening? The bike is now moving faster. So the distance between them will start decreasing. So for example, analyze at t equal to 6 seconds. What is happening? By now the bike is moving at 12 meters per second, whereas the car is continuing to move only at 10. So now you can see the distance between them, it starts decreasing. So ds by dt should be negative. And that is what the graph is showing us, that at 6 seconds, ds by dt is negative. Okay. And like that, it is going to reach 0. That means the bike is going to come alongside the car, just going to overtake it. Will happen at some time, which we can calculate by making the s equal to 0. That is 50 plus 10t minus t square should be equal to 0. So one root of time will be negative, that we will not take. The positive root of time will be 10 into 2.73 divided by 2. So that is 10 into 1.36 something. Okay. So 13.6 seconds approximately. So that is the time when this would have happened. The s would have become 0. So this is the time when s is equal to 0. So the overtake happens. But between 0 and 13.6 seconds, what is happening? For the first 5 seconds, the car is actually moving away from the bike because the bike is taking time to pick up speed. 5 seconds onwards, the bike has become faster than the car. So it's catching up. Okay. And finally, it manages to catch up at this value of time, which is 13.6 seconds. Okay. And there's another negative root, but that is not significant for us because negative time is not taken into consideration. And meanwhile, it reaches this maximum distance of 75 meters, whereas it started from 50 meters. Okay. So hope the whole analysis of this question is clear.
Yes, sir.
Okay, people. So this is an example of how, calculus and the analysis of functions in terms of maxima, minima, behavior of the function, etc., is used in an actual physical situation. So word problems of application of differentiation, application of calculus that we had seen in the previous few lectures, differentiation as a rate measurer, application of chain rule. Now those type of problems will be extended to even situations where we have to do analysis of maxima, minima. Okay, so we are at this stage now done with differentiation and its applications. Okay, obviously, like I'll be sending you worksheets and a lot of questions to work out, and we'll discuss some doubts and questions too. But now we are in a position to start with integration concepts in the next lecture. So we'll be doing that also. So that's it for today's session, people. I will send you a list of all the questions of differentiation that you can now complete from the module, as well as a fresh worksheet, which will have problems related on maxima, minima, domain range, as well as few revision questions from chain rule, etc. Okay, so make sure you work that, and also hope you have all finished the revision worksheets by now, which I had given before the test. There were quite a few questions in those revision worksheets put together. So hope all of those are completed. If there are any doubts, then just keep them noted down. We'll discuss in the next lecture. Okay, that's it for today's session, people. Wish you all the best. Thanks for attending.
Bye, sir.
Thank you, sir.
Thank you, sir.
Thank
I
you,
just
sir.
had a question.
Yeah, Vita, tell me.
Sir, could you tell me how to calculate the tangent line at a given x coordinate?
The tangent line at
At a given x coordinate, say
for a
x is
function,
equal
how to find the equation of tangent, you're saying, no?
Yes, sir.
Okay, so let's take just an example. Suppose we have this simple quadratic function y is equal to x squared plus x plus 1. Now I ask you that find the equation of tangent at some point, let's say x equal to 1. Okay, so basically what I'm saying is, that roughly speaking, the graph of this function will be looking something like this. Okay, so at some point x equal to 1, let's say that is over here.
So I cannot see your screen if you're sharing it.
Oh, sorry. Yeah, you can see this now?
Yes, sir.
Okay. So I want to find the equation of tangent at this particular point. So what I'll do is, first of all, I'll find the coordinates of this point. So x equal to 1 pe y ka value kitna ho jayega? It is 3. So this point that I'm talking about is 1, 3. Got it now?
Yes, sir.
Now I want to draw a tangent line at this point. So the tangent line is passing through this point, but it has a slope of how much? So this tangent will be a line of slope m equal to the value of dy by dx for the function at x equal to 1. So the function, so that means the slope of the tangent will be equal to f prime x at x equal to 1. So given this function, what is f prime x? We'll first find that out. So f prime x is 2x plus 1. Okay, so you can see that at x equal to 1, f prime's value is 3. Right? So the slope of the tangent will be equal to 3 and it passes through the point 1, 3. So how do we find the equation of a line which has this slope and passes through this point? It will be y minus y1 is equal to m times x minus x1. Got it now?
Okay, sir. Thank you.
Okay. So any function in place of this, you can now repeat this analysis. Right? So first find the coordinates of the point for which the x coordinate is given. So that is, let's say, x1 and y1. Okay. And then find the slope of the tangent at that point. That is the value of f prime at x equal to x1. And then use the general equation of line that y minus y1 is equal to m times x minus x1. So this is the equation of tangent at x equal to x1 for the function fx. Okay, beta, hope
Okay,
this is
sir.
clear. Yeah.
Yes, sir. Thank you.
Okay.